When we talk about the forces that shape our universe, gravity and electromagnetism usually steal the spotlight. Even the strong nuclear force, known for binding atomic nuclei, is often more recognized. But today on Infinity Beyond, we turn our attention to the unsung hero of the cosmos, the weak nuclear force. Despite its misleading name, this force plays a profound and irreplaceable role in the evolution of the universe, the formation of elements, and the very spark of life. So, what exactly is the weak force? It's one of the four fundamental forces of nature, alongside gravity, electromagnetism, and the strong nuclear force. As the name suggests, it is much weaker than the strong force or electromagnetism. But don't be fooled. Its subtlety hides immense importance. The weak force operates at incredibly short ranges, less than 10 to 8 meters, shorter than the width of an atomic nucleus. And unlike other forces, it doesn't bind or attract in the traditional sense. Instead, it's responsible for transformations, for changing one particle into another. This force is behind radioactive decay. To the average person, radiation might seem dangerous or destructive. But in the vast cosmic picture, radioactive decay is a creative force. It allows unstable atoms to transform, releasing energy and forming new elements. Without this process, stars wouldn't shine as they do. Elements wouldn't change. Life wouldn't evolve. Let's zoom in. The weak force is the mechanism that allows a neutron to decay into a proton, an electron, and a neutrino. This process, called beta decay, is a cornerstone of nuclear physics. It's how certain isotopes stabilize themselves and how stars evolve through their life cycles. But more fundamentally, the weak force enables quark transformations. Quarks are the elementary particles that make up protons and neutrons. The weak force is responsible for flipping one type of quark into another. For instance, turning a down quark into an up quark, effectively converting a neutron into a proton. This process releases an electron and an elusive ghost particle called a neutrino. These neutrinos, produced in astonishing quantities, zip through the universe at nearly the speed of light, rarely interacting with anything. Every second, billions of neutrinos pass through your body without you even noticing. They are messengers from the heart of stars, from supernova explosions, and from the birth of the universe itself. Without the weak force, neutrinos wouldn't exist. Beta decay wouldn't occur. And the cosmic evolution we take for granted, element formation, energy release, even biological processes, would be impossible. Let's bring it back to the stars. Inside stars like our Sun, the weak force plays a key role in the proton-proton chain reaction, the process by which hydrogen atoms fuse to form helium and release energy. This is how our Sun generates its light and heat. The first step in this fusion process involves the weak force converting a proton into a neutron to form deuterium. Without that transformation, the chain reaction would never begin. The sun would not shine. Imagine a universe without sunlight, without stable energy sources, without warmth. That's a universe without the weak force. And beyond stars, the weak force played a vital role in the early universe, specifically in Big Bang nucleosynthesis. It helped determine the balance of protons and neutrons in the first moments after the Big Bang, which in turn shaped the distribution of hydrogen and helium in the universe. Even now, on Earth, the weak force is part of our daily lives, whether we realize it or not. It powers the decay of radioactive elements deep inside Earth's crust, heating the planet's interior and driving plate tectonics. It influences nuclear reactors, medical imaging, and carbon dating, all by enabling atoms to transform over time. And while the weak force may seem elusive, scientists have captured and measured it through incredible experiments. In high-energy particle colliders like CERN's Large Hadron Collider, researchers observed the weak interaction at play in W and Z bosons, the force-carrying particles responsible for mediating weak interactions. These bosons are massive compared to photons or gluons, which is part of why the weak force is so short-ranged. It takes immense energy to produce or detect them, but they are real, and their discovery helped complete the standard model of particle physics. But the weak force still holds mysteries. It's asymmetrical. It violates something called CP symmetry, which relates to matter and antimatter behaving the same way. This asymmetry might help explain why there's more matter than antimatter in the universe, why we exist at all. In that sense, the weak force could be one of the most cosmically biased forces in nature, and thank goodness for that. Without that tiny preference for matter over antimatter, our universe might have self-destructed into pure radiation. Instead, here we are. Atoms formed, stars ignited, life emerged. All thanks in part to the invisible transformations orchestrated by the weak nuclear force.